Theoretically, what if we moved it over? If we moved the carbon-carbon double bond one carbon over, moved it closer, would the bromine be sitting on the 4 carbon at that point? Here it'd be on the 1, 2, 3 carbon, so we then have to move the bromine a carbon away, and the cycle would continue. So no matter where you place that double bond, the bromine must always be on that 4 carbon. So whatever structure you draw, it will always have bromine in this configuration, because you can't put the double bond any closer and you can't move it any further away. It has to be sitting there at that 4 carbon with respect to the carbon-carbon double bond. Any other questions on this guy? Any other questions on the ring, on the ene, on the bro? Any questions on this guy? Alrighty, solid, solid, solid. And now, oh goodness gracious, this guy. This is the guy I'm sure that's probably going to stump everybody because one of these functional groups is going to get misplaced. But let's try to break this guy apart and try to avoid putting the wrong things in the wrong place. Alright, so again, we start out with our carbon chain, right? So what is it? It's a cyclohexane, so it's the exact same thing that we had in the previous drawing. But now, is there a double bond in it? No. The ane ending tells us there is no double bond in here. So I can just draw the generic cyclohexane, or hexagon for science. So we got the cyclohexane part down. Okay, that makes a lot of sense. Alrighty, so now we identify what substituents we've got. Okay, so we have a methyl ethyl, and then we have just a plain methyl. Now it tells us here that our methyl is sitting on the 1 carbon, and the methyl ethyl is sitting on the 4 carbon. So again, numbering here is strictly up to you. I like to start numbering at the top of the ring if possible. So up here, I'll say this is our 1 carbon, so to speak. 2, 3, 4, 5, 6. So there's my ring, and I've numbered it 1 through 6. I numbered it just regular clockwise. Nothing too terribly bad there. So we got a methyl sitting at the 1 carbon. So I'm going to put the CH3 up there. And then what is a methyl ethyl? What is that? It's basically the equivalent of an isopropyl group. It is just an ethyl with a methyl coming off of it. And this would be the attached group, wherever it's attached. So this guy right here is a methyl ethyl. It's the IUPAC, favored name for this guy, but you guys have seen it as isopropyl as well. That's all it is. And we have that guy down here, pretty much, sitting at the 4 carbon. Now, I've intentionally not stuck them to the ring yet, because what else have we not taken into account yet? The cis part. So, what configuration do these guys need to be in? Same plane, same side. So does it matter if they're both wedged or both dashed? No, so we can draw them both dashed or both wedged. I think the answer key has them as both wedged, but you can also draw them as dashed. I'll put that on the side here as well. You could also put them as both dashed. As long as they're on the same side of the ring structure, you're going to be fine. Any questions on this guy?
What is the 1 from the methyl ethyl?
Good question. So what does the 1 from the methyl ethyl mean? So this is nomenclature within nomenclature. So basically what's going on here is that you have a methyl group, so to speak, attached to the 1 carbon of the ethyl group. So if we draw out the methyl ethyl separately, right? So the ethyl actually is only 1 carbon long. But ethyl is 2 carbons long, so we have 1, 2. So you have a methyl group attached to the 1 carbon of the ethyl group. So technically speaking, oh, actually there is another carbon here. What am I doing? Yeah, this would be the carbon it's attached to. Okay, I just confused myself. But yeah, so this would be the group that the ethyl is attached to, 1, 2 carbons. So if we number this out 1 to 2 carbons, at the 1 carbon we've got a methyl attached there. So that's what the 1 is signifying for us, is that that methyl group is attached to the 1 carbon of the ethyl group. But just as a rule of thumb, that one right there is technically redundant. Because if you put the methyl on the 2 carbon, what does it technically become? It becomes a continuous 3 carbon chain, it becomes a propyl at that point. So if you have a methyl ethyl, the only real way it can be attached is at that 1 carbon. That 1 there is just thrown in there just to, again, be redundant and to be excessive. If the methyl is attached anywhere else, it's a propyl group at that point. You can't really call it methyl ethyl. But good question though, good question. Does that make sense though? So the 1 is there for a reason, it's just kind of a stupid reason. But any other question on this guy? Alright, so let's swing on down over here. Oh boy. How glorious is this? Let's see who can remember their suffixes. What's this? Yep, diol. That is 2 alcohol functional groups. And where are they? 2 and 6. So if you guys forget about your suffixes and forget that a diol means 2 alcohols, look for the numbers. So it's like, okay, so I got an alcohol in here, but I see 2 numbers here. So that means there's got to be 2 alcohols in here. And all right, heptane. So how many carbons long is our chain? It's 7 carbons long. So let me just see if I can draw out a nice 7 carbon chain here. 1, 2, 3, 4, 5, 6, 7. Bingo, yay, there's a 7 carbon chain. And we have 2 alcohols, right? So 2 times OH. And we have them sitting at the 2 and 6 carbons. So 1, 2, so there's 1 alcohol here. 3, 4, 5, 6, here's the other one. Makes sense so far, right? So all I've done is drawn out the 7 carbon chain, and I've placed both alcohols in there. And what else do we have here that we have to draw in? Yep, we have dimethyl. Now, this one gets really tricky. I know it looks pretty straightforward. Okay, that's dimethyl. Some students who get in a really, really big rush will read this as dimethyl. Now, that's not an actual thing, but I've seen students say, okay, dimethyl, that means we have 2 ethyl groups in here. No. Separate the prefix from the rest of the word. I don't want to see a dimethyl, which I'm guessing is the opposite of a lit ethyl. That's my big guess there. But it's 2 methyl groups attached to, which 2 carbons do we have them attached to? 2 and 6. The same 2 that the alcohols are attached to, so I'm just going to stick them right here. And that's it. Nothing too bad, right? Drawing out 7 carbons is probably the most complicated part of this one. Just make sure you keep track of your carbon number. But any questions on this guy? Any thoughts, concerns, issues here? All right, we're blazing through the nomenclature. Again, these guys should mostly be review. Okay, well, this should look familiar. What kind of carbon chain is this? It's 7 also, so it's going to have the same general structure as this guy. Okay, boom, so I drew him back out again in an uglier form, but still 7 carbons long. And what do we have attached to it? We got 5 methyl groups. Oh, look at that. There's all the numbers. 2, 2, 4, 6, 6. Wow, so all we're doing is just stuffing 1, 2 methyls there, 1, 2 methyls here, and then we're stuffing a 5th one here in that middle carbon. 1, 2, 3, 4. Looks like a creepy looking spider, but yeah, that's it. That's all there is to this guy. You're literally drawing nothing but lines. No letters involved. You're literally just drawing lines here. But any questions on this guy? Like, he may seem simple, but if there's any thoughts or concerns you guys have on him, I can gladly try to clarify them. On the final, will he likely...
So for the two, can we just draw the lines like this instead of like one on top?
Good question there. So for our 2,2 methyl, or the other ones, could we draw the methyls like this? And the answer is yes, we can draw them like this. It's perfectly fine. But now a question here is like, oh, well, for the sake, for this practice final, he keeps the carbon chains that are pretty large, roughly the same, length and size. Will he do this on the final? And the answer is most likely. He will more than likely try to get you to draw a really long carbon chain and then just have you duplicate it in the box next door to it. So instead of a heptane, it might be an octane you have to draw, or a nonane, or a decane. But it won't be anything that's higher than, like I said, for the most part, 13. He threw the 13 in there just to spite me. He did that on purpose. But, again, so there's some repetition here, and like I said, as long as you guys understand your nomenclature, you guys will be fine on that very first page. Which is sad, it's only worth 12 points, which is, yeah, a very small chunk, but points are points. Now, are there any other questions on this entire page? This is your nomenclature summary right here. You get to touch a little bit of everything. Alrighty, so that's page 1 down, yay! And now, you're gonna get hit with stuff you guys haven't seen before on the very next page. But you guys have seen it, you guys haven't done a whole lot of practice with it. But okay. So we got ourselves a nice little alkene here, and we're tossing some elemental bromine at it. Now you guys haven't seen a whole lot of reactions involving bromine with alkenes. Basically what happens is you end up with 2 bromines attaching to your structure. One on each side of your carbon-carbon double bond. And they're going to be on opposite planes of each other. Because again, the arrow pushing forward is a pain in the butt. You guys don't really need to know that. But you end up with a weird bromine intermediate that ends up getting pushed over to one side when one of the bromines attacks via backside attack. But basically you're adding a bromine to each side, and it's going to be they're going to be in the trans configuration with respect to each other. And the big hint there is the large box, plus you have to describe the relationship between them. So just know if you see an alkene, and you're adding Br2, you're just adding 2 bromines and they're going to be trans with respect to each other. Not too bad, right? So we're attaching 2 bromines to our structure here. But now here's where things kind of get tricky when it comes to drawing this, because right now those 2 carbons that are right there are not stereocenters, so to speak. But the addition of the bromines on each side are going to make them stereocenters at that point. So we have to keep an eye on where the methyls are and where the hydrogens are before we add the bromines. Now we could say, one bromine is wedged and one's dashed. But to make life a lot simpler, we tend to just draw the bromines physically trans with respect to each other without the usage of planes if possible. So there's the generic backbone, we draw the bromines trans with respect to each other. And obviously one come up here, one come down here. We could have 2 different ways that these bromines could attach here. So that's how we get 2 different products here. But now we got to go back and assign some planes of orientation for our methyl and for our hydrogen. Now, before we turn this into a stereocenter, these methyls were on the exact same side of the structure. So when we transfer it over to our products, that means they both have to either both be dashed or both be wedged. Now I think if just for the sake of the answer key, he draws them both as wedged. But you could draw them both as dashed as well. And then we don't draw the imaginary hydrogens there. But again, the reason why these guys are both wedged is because they were on the same side of the structure before the bromines attached. That's not going to change simply because we add 2 additional functional groups. But yeah, that's basically the 2 we could have. And obviously we could draw the same structure, but with both methyls being dashed instead of wedged. But does that make sense so far? Like I said, when you get an alkene, you're tossing bromine at it, you're getting both bromines attaching, but again, in the trans configuration. Because what you technically end up with, if I draw just the generic structure for an alkene, you end up with a weird and very, very ugly and very unhappy bromine molecule sitting in an intermediate like this. Basically, the alkene attacks the bromine, and you end up with this weird, ugly mess. But now notice this looks a lot like an epoxide. So notice that when the second bromine comes along, it's going to be negatively charged.